In a world where the laws of classic Newtonian physics breaks down and uncertainty is a principle, one skunk will find himself trapped in a world he doesn't understand.
Oh my goodness, I sure got us into it this time. Do you know where we are? Oh goodness, I hope we figure it out soon. But wait, where's Davis? He was right behind me a second ago.
Well, hey there, Morkie. Well, we sure got ourselves into it this time. Looks like we're trapped in the quantum realm.
The quantum realm? But Davis, what is the quantum realm?
Well, Morkie, the quantum realm is a place, or more accurately, a size, where objects begin to disobey some of the laws of the regular physics that you and I listen to. Down here at the size of atoms, distances of hundreds of nanometers, objects obey a different set of rules, quantum mechanics.
Size of atoms, eh? Is that what all this weird stuff floating around us is?
That's right, Morkie. We're surrounded by atoms. Down here at the quantum level, we can see the electrons orbiting around the nucleus in a specific sized shell we call an orbital.
Whoa, those electrons sure do like to dance around. It looks like they never stand still.
That's right, Morkie. It's because electrons are both particles and waves. It means they behave a little bit differently than other objects. Here, let's snag an electron and I'll explain.
Whoa! This feels weird, Davis.
I bet, Morkie. That's because that's a subatomic particle you're holding there.
Whoa! Then you take it.
All right, Morkie, I'll explain. Electrons can exist at a set of specific energy levels, which is what defines an orbital. When electrons gain or lose energy, that's how they move between the orbitals.
Well, that's great and all, Davis, but I don't understand how that's going to help us escape the quantum realm.
Well, Morkie, if you hold your horses, I'll get there. Now, electrons don't move between space the same way you or I might take an elevator to move between the floors of a building. Rather, they tunnel through space.
What do you mean, Davis?
It's an effect called quantum tunneling. It means that electrons can move through barriers rather than having to go over them. Here, take this electron and I'll explain. Try to walk over this hill.
Well, this sure is a lot of work, Davis.
I bet, Morkie, that's because this hill represents a classic energy barrier, like the energy gap between orbitals or the space between the floors of a building. If an electron were a regular object, you would have to walk it over the entire hill like you just did. But down here at the quantum level, it can tunnel straight through.
What, you mean I didn't have to walk all this way?
No, you didn't, Morkie. Here, I'll explain. All I have to do is give this electron the right amount of energy, and it will tunnel straight through our barrier like this.
Whoa! But what is it that allows electrons to do this, Davis?
Well, Morkie, it's the fact that electrons are both particles and waves. Under classic physics, a particle hitting this barrier would come to a stop, but an electron can tunnel through.
And that's gonna help us get out of the quantum realm?
That's right, Morkie. In my lab, I have a special microscope. It works off the principle of scanning, tunneling microscopy. In it, we take advantage of electron tunneling by scanning over a surface with a needle filed to the point of a single atom. By applying an electric current to that needle, I can get an electron to tunnel from the surface to my microscope.
Well, why the heck would you want to do that?
Because, Morkie, I can detect individual atoms on a surface and map it. It's a microscope that can see at the resolution of atoms. And that's how we're going to get out of here. All we need is enough energy to tunnel us from here on the surface to my microscope. But where are we going to get enough energy, Morkie?
Well, these fine folks certainly look like they have some energy.
That's right, Morkie. Maybe they'll help us. Look, we're going to need lots of energy to escape this mess.
So on the count of 3, if you would all please stamp your feet as loud as possible.